Pre-made, yeah. You kept the
I have a videographer.
You have a videographer? Can I be a videographer? Please. Come on, bro.
You'll go with please first.
Bro, I.
Where is it? You like this number?
What did you say?
Where's Andrew?
What told you, bro? So, yeah, this is, number 4 is down.
I don't even know if we get through this shit, so I don't know like that. Yeah, dude, that was kinda like, I don't know why, but everybody's complaining way more than usual yesterday. Just, they were complaining so much.
Who were?
People.
Yeah,
Like,
photos?
yeah.
Did you know that Duke Lewis from World F? Did you and him ever come together?
Hello everyone. Is there any event going on today? On campus? Any? Today we are still on chapter 17 on the textbook, and as you see in the textbook has some topic that we covered on quality control. We're gonna have a quick review on those topics. Skewness is one of the parameters that we pay attention. We want to make sure that factor is going to be taken care of, because that measures the asymmetry of the distribution, right? It has a coefficient and ranges between -3 to +3, okay? As you see, it has negative number and no positive number. So if you have a symmetric, this distribution, your data are in bell shape, normal distribution, the peak is right in the center. Remember we talked about couple, mean, mode, the median, and all those, factor right in the center, then you have a skewness 0, okay? Once you have a 0, that means your normal distribution is perfect, but you may have sometimes, some negative skewness or positive skewness. And we can also, calculate these, factors. There are different ways to do it. This is the Pearson coefficient of skewness. In this course, you're not supposed to, I'm not gonna give you a problem to calculate the coefficient of a skewness. This is just a review, okay? This is another way to do it. Also, we can use Excel software. The function on the Excel is called SQKEW. Okay? So when you have a positive, skewness, number is 1, how does it look like? So that tail is gonna be toward the positive direction. If it is negative, the factor skewness is negative, so the tail of that distribution is gonna be toward the left, like this one, as you see. This is positive, it's going this way, right? And this is negative, that tail goes the negative direction. So if you have symmetric, that means your skewness factor is 0, so you have a perfect bell shape. Sometimes you may have the by model, this type. Okay, another factor that we use to look at that distribution is called kurtosis. Okay, kurtosis measures the tailiness of the distribution, right? How thick or how flat your distribution is. If you have a factor around 3, that distribution is normal. Okay, not only the previous skewness you have to consider, but also you need to look at this one, kurtosis. Okay, so number 3 means your normal distribution is normal. And if you have a higher number, more than 3, that means you have a heavier tail. It's called leptokurtic, and meaning more value are concentrated on the tail rather than on the center. So this one. And you have a lower kurtosis, then means you have platykurtic, meaning distribution have fewer extreme value, and your distribution is going to be more flat, not that bell shape. I have this picture that shows these 3. So this is the normal one, mesokurtic, right? The normal distribution. If you have a larger tail, this is when you have a number more than 3, leptokurtic. And this is flat, your that or all over, right? Flat is correct. Any question? In the textbook, they have equation, for both factors, but in this course, I'm not gonna give you a problem for finding, this kurtosis or the other factor. Any question about this topic? These 2 factors? No? Next topic, central limit theorem. This tells us when you have, we take a large number of random data from any population, the average of the sample are gonna be like a normal distribution. So if you increase, this is when you have lower data point. See this one, you may have 5 data points, 10 data points, right? As you increase, you will have better distributions, which is going to be similar to normal distribution, right? Even it says even if the original data isn't normally distributed, as we increase the sample size, the number of data, right? The sample average become more and more normally distributed. Look at this example. The sample size, for this one was 2, 4 has been increased. The normal, the number of minimum, the sample size should be about, in the textbook it says it should be around 30. Okay, so this is 30 sample size. As these increases to 100, it's become more that the normal distribution shape or the bell shape. We can test it. We have one animation. You see this? Wait, it doesn't show. see this animation. You see, we can drop a ball from top, right? And the first time, it's gonna be random. It can go any of these, spot, right? And then this one, we can increase the number of rows. For this one, we have 12. The binary probability is going to be 0.5. Let's drop 1. So it went there. So we have one data here. As we increase, let's see where the next one goes. So this one got 2, right? So it's going to increase based on the occurrence. So I can pick, also this one shows the path. This is more fun. So I'm gonna pick this one, it's gonna drop a lot of ball and then see what happens. So this is the number of ball. As you see, as it increases, we'll get that bell shape, right? Eventually, again, it depends on the number of samples. I can also show this, ideal one. So this is the ideal, and this red cell approaches that blue line. Blue rectangle. I don't know if it has a stop.
If you hit the start button,
Oh yeah, got it. No, if I stop. So based on this number, we got this shape, right? Interesting. And it tells you also the average. If you change the binary probability, so also that's going to affect this shape. So it means there is a tendency. So it's going to go, it's going to shift. The center is going to shift toward this way or the left. Any question? So this is that concept. As you increase the number of samples, then you will have that bell shape. Okay. So that distribution is called normal distribution. That bell shape. Sometimes we call it Gaussian distribution. And we show it with this equation. Normal distribution. Actually, this should be x. Let's do this one. This is a normal distribution, as you see. And we sometimes we want to find how many of samples are within a certain range. Let's say this is x1, sample 1, and this is 2, right? We want to see how many data we have within those 2. You may have 10, 3, depends. But it's going to be difficult to find, those numbers, right? This normal distribution. Then what we do, we transform it. We transform it to a standard, normal distribution. In the standard normal distribution, what we have, this is the average. Right? This is the average of your data points. And you may set, USL, upper limit and lower limit. But if you want to find, the probability of sample within a certain range, then it's better to transform it to a standard normal distribution. What is a standard normal distribution? In the standard normal distribution, the average has to be 0. So you have an average in your manufacturing, in your process, you have a certain average. We want to transform this one in a way that that average is going to be 0, right? Then we use this transformation, this one, normal distribution. So this here we have x. Then we're going to change it to a new term called z, and that z is a function of x, this number, minus mu average, sigma standard deviation. Okay, you calculate what is the standard deviation for your sample, you put it there, and then put average here, then it gives you z for every point. So this z1 corresponds to x1 in this distribution. Why do we need it? Why do we need to transform it? Because you want to find the, in order to find the probability, how much, what is the probability of between these two, you have to measure, you have to calculate the area, right? The area for every graph, you have to then go to integral, calculate all those mathematical equation. But once we set it to this one, this is a standard. We can construct a table. There is a z table. You can go to the z and find the average. You can find the z for the area for every z. Then it's going to be easier, less hectic, less tedious to find the probability, because that is, you have one standard, one table to find the area. You don't need to go to this equation and find the integral of this equation to find the area. So this one, we call it probability density function, and this is the new equation, because we substitute this term with this one. Now this is z. Okay. Again, you don't need to calculate integral of this one. We use what is it? Table, z table, to find the probability. For every z, we have this area. So I'm going to show you how to calculate this one, and it is called a cumulative distribution function. Let's say we want to measure, we calculate the probability of having x1, let's say 2, okay? Then you have to find z corresponding to this x1. You put it into that equation, this equation, right? You find z, and you come here, z. This equation, this one, gives you the area before that point. So this area under the line. The area under this line will be given to you by this equation, which is in a table, right? If they say tell you what is the probability of having x1 in this process, you go find the z corresponding to this one, which is here, and then go to the table. Tables gives you the area. If they ask you what is the probability having parts within x1 and x2, right? Then what should we do? So this, you have to calculate the area twice. So this is you find the z for this one, right? That gives you, then go to the table, find the area here, right? and then you find the area for x2 based on this z2. What else? You have to subtract them from each other because z2 covers this area. Let me write it here. This is worse. Okay. So Z1. This is going to be Z1. You find probability of Z1. Okay. And then you find the probability for Z2. This probability of Z2 is going to cover all this area. I'm gonna maybe it's better to use different color to distinguish. Even this area. Okay? It's gonna calculate the area, under this curve up to that point. So it's gonna cover even this portion, right? But our area of interest, where was it? Between Z1 and Z2. So we have to, do this way. Probability of this area, this portion, is PZ2 minus PZ1. Okay, for this area. Any question? How about probability of point x3? At this point above z3. Let's say I put z3 here. I have a Z3, and I am interested only in this portion. How can I calculate this area? The probability for this area. They call it probability, right?
You change your value from Z to infinity instead of negative infinity to Z.
Negative infinity to the Z3, right? We calculate that one, P, Z3.
Yeah, it means Z to infinity, because it's going to the right.
Right, it's gonna come from this area. It will give me, when you go, calculate this one, that will give you the entire area. What is this entire area? The entire area is gonna be probability, always, entire area is 1, the entire portion. So what we do, you calculate this portion, right? Minus 1. So that gives you this area, right? We call it, if it is USL upper limit, upper specification limit, we call it, scrap rate, scrap. Or this one might be, it depends on your, engineering products, right? If you are working with, let's say, a gear, and it has a internal diameter beyond a certain size, right? Then you cannot, work on it, right? So if it is beyond a certain size, it's gonna be something like that, a scrap. If it is less than a certain size, then if it is here, it's called a rework. You can send it to another station to work on it and fix it. It's called rework. Z table, they are available online. Also, I put it on the Canvas. There are programs that calculate Z for you, that probability, right? You put your information, average, standard deviation, and any point of interest, right? The X. Based on those three information, it will give you the probability for any certain point. So this is what I said before. LSL, lower specification limit, and this is upper specification limit. Depends on your production. Let's say we want to find the percentage of value between 40 and 60 in a distribution that has an average of 50, right? And a standard deviation is 5. What is mu here? The mu or average is 50, correct? That was given up there. So in the first step, you have to write, the information, summarize it, what you have. So it says, find the percentage between 40 and 60. And distribution has a mean, mu, correct? What else? A standard deviation is sigma, is 5. So this is my normal distribution. Is it when I put 50? Is it normal distribution or a standard normal distribution? So this is my raw data. 50. Average mu is 50. That means this is my normal distribution. When you use that z function, x minus mu divided by sigma, and then convert it to a normal distribution, a standard normal distribution, that the center is 0, this is called the standard normal distribution. This is a standard, this is normal. Question? This is 5, sigma is 5. The standard deviation. Now we want to find percentages, between 40 and 60. It means, 40 here, right? This is 50. Where is it that we are interested? This area. Can we calculate this area in this problem? No, in this normal distribution? No. We have to go to here, to this one, because the z is given for this, the standard normal distribution, not for this one. So what is the z corresponding to this one? 40. You have to calculate it, right? You use this one, right? X 40 minus what? Average 50 divided by 5. So this is my new z, right? Z1. And how about 50? I'm gonna find it here. Again, this should be 60, right? 60 minus 50 average, then 5. So these are my new z. Then I have to use this, z number to find the area. Okay. How? So once you divide this one, this is gonna be 10 minus 10, this is minus 2, right? How about this one? This is a 60, 10, positive 2. So I have Z1 minus 2, Z2 positive 2. Again, so in order to find this area, I have to find P Z2 P Z1. If I go to my table, let's see where is it. Table. I uploaded, so this is. Here. So number 2. Number 2 has this number, right? Negative. So the probability, that area for this is this other. What was this one? PZ1? Point 0228. Right. And how about the plus 2? Plus 2 is here. Oh yeah, this one, right. 0.9773. Do you agree? Everyone agree? Okay. If I had, a number like 2.01, what would be my, area? 2.01. So you see, you have to go that one. How about I have a number 0.2015. Can you find it? The area and the probability for that Z. This is here, right? And then 0, this is there, 1, right? So it's between these two. So you have to take the average of these two, the middle of this number. Right? This is very, a small trick. Make sure sometimes in the problem, in the exam, you see, oh, I don't have it, so I cannot solve this problem. No, you can solve it, you can continue. Just take an average of this, 2. Clear? Okay, what was that? 29773. So the probability, you just subtract these two from each other, and then find the answer. Maybe I have it. About 0.95. So if you find some number that is more than 1 or less than 0, you double check. It should be always between 0 and 1. Okay? It cannot be more than 1 or it cannot be less than 0. So this is a rate, So you can multiply it by 100%, multiply by 100%, then it will be, percentage. 95. This is percentage. Any question? Blue, you got question? No? Okay. Defects, defects. Okay. So this is one exercise before I give you the class activity. I'm gonna solve this. Let's do it together. Anyone interested in solving it? Okay. The manufacturer of CD, following this specification, the diameter, internal diameter, I should have changed that here, because always for mechanical engineering we see a symbol like gear. It's not always gear, right? In mechanical engineering they work with a lot of different parts, but that symbol for mechanical engineering they show it here. So I wanted to change it to CD, but I forgot to change that the other way. Okay, so it has an internal diameter of 0.75 plus minus 0.005 inch. Okay, that is a tolerance. Below the lower specification limit, the company must reload the part on the machine. So what is the specification limit for the lower one? You can accept the part if the part is within this range, right? So DIT is 0.75. 0.75 minus 0.05 will be
0.745.
huh?
0.745.
Point. Right? And this one 0.755, right? So this is my specification limit. Upper and lower. This is upper, right? And this is the lower specification. Okay. So basically, if the part is outside this range, we cannot accept it. Okay. Below the lower specification limit, below this one, it is called rework side. Above this one, it's called scrap. We cannot use it. Calculate the expected percentage on the rework side. We want to see, this side. We have to construct that, take, the normal distribution and the standard normal distribution. What is this one? Average. The average is this much, right? 0.75. What is this one? It's mu for average, correct?